here we are in the last lecture about Laplace transform and also the last lecture of the course. Okay, we start. So the goal of this lecture is to solve some ordinary differential equations applying the Laplace transform, as I said in the previous lectures. Okay, to this aim, let's recall the Laplace transform definition and its main properties. For more detail, you can see lecture 9. So, Laplace transform. Here we have a definition. We have a function f of t with t not non-negative, and the Laplace transform of this function f at some s that in principle is positive is here is just the definition, the integral from 0 to infinity of the function f times exponential to the power minus s times t, differential t. Okay, so just observe that here we have the variable t and we are integrating in t, so this, as a result, this function depends on s. That's why we have here this guy. Okay, some properties. We have linearity of this Laplace transform. We have this other property that powers of t go to derivatives in some sense. And what are we saying here is exactly this formula that we have, that if we want to compute the Laplace transform of a power of t times a function, then this goes to the Laplace transform of the function f, and this power of t goes into this derivative here with this minus to the power n. Okay, other property, that exponential functions go to shiftings, meaning that we want to compute the Laplace transform of a function f times an exponential. So these go to the Laplace transform of f, and the effect that this exponential function makes is this shifting here, minus alpha. Okay, some examples that we saw in lecture 9. The Laplace transform of the function 1, which is 1 over s. Function t is 1 over s squared. The exponential function is 1 over s minus alpha, which of course coincides with taking this Laplace transform and using the property that exponential functions goes to shifting. You can check that also. And a power of t, we know we use the gamma function to compute this Laplace transform last lecture. And a bit more general, for any alpha greater than minus 1, we have this Laplace transform. Then using Euler's formula and properties of the Laplace transform as the definition and the linearity, we also got the Laplace transform of the cosine of alpha t and sine of alpha t, being these two guys here. Okay. Last property, but not the least, it's important, how the Laplace transform acts with derivatives of the function. So for the first derivative, we get the Laplace transform times s minus f at 0. For the second derivative, we get s squared times the Laplace transform of f and this polynomial of order 1, which goes like one derivative before, until one derivative before. For 3, we have power 3, the Laplace transform of f, and this quadratic thing, polynomial here. And for any n, we have s to the power n, the Laplace transform, and this polynomial here. Okay. So, we also saw how to undo this process, so how to compute the inverse Laplace transform. We know that this inverse operator is linear, and we saw how to find the inverse Laplace transform of this special family of functions, rational functions, which means that we have a function which is two polynomials consisting one polynomial divided by the other one, and these guys have like the one that is here, p, the degree is less or less, strictly less than the degree of q. And we know how to obtain the partial fractional fraction decomposition of this expression, which makes easier finding the inverse of such a function. Okay, so that was everything we learned last lecture, and now we apply all this knowledge to solve some ordinary differential equations. Okay, so we call, of course, this method that we are going to see now the Laplace transform method. And as I said last time, this is super similar to the Fourier transform method. So we describe the process via these three main steps. Step 1, we Laplace transform the ordinary differential equation. Step 2, we use the initial conditions to find the Laplace transform of the solution of the original ODE. Let's say, just to fix notation, the Laplace transform of a function called yt, y of t. Step 3, we find this y of t computing the inverse Laplace transform of the solution we obtained in step 2. And here you can see the similarity with the Fourier transform method, because it was Fourier transforming the partial differential equation, so we would change this Laplace by Fourier and this ODE by partial differential equation. Then we were using initial condition, and well, we were solving the equation that we found in step 1, and then we were undoing the process, so we get the real solution and not the transformed one. So the steps are quite similar. Let's see this method in a couple of examples. We have to solve this ODE, which is a second order linear ODE with constant coefficients, non-homogeneous also, and we have these initial conditions. Okay, we have to solve this with the Laplace transform method. We of course we know how to solve this with like from the beginning of the course, with I don't know, the characteristic equation for the homogeneous one, a particular solution, and so on. But now we really want to apply this Laplace transform method. So step 1, Laplace transform the ODE. So this is our ODE, and we Laplace transform the ODE. So we have to compute the Laplace transform of this side of the identity and the other side. Okay, so now we can use the linearity of the Laplace transform to split the sum, and of course we can also put out these two. So we have the Laplace transform of the second derivative of y plus the Laplace transform of y equal to 2 times the Laplace transform of the function 1 in S. So after we start with the ODE, we use the linearity. And now, for instance, in this piece, we use that we know this guy. We computed last lecture. So we use this well-known Laplace transform. And here we use the property that relates derivative of functions and Laplace transform. So we know that this guy is exactly s squared, the Laplace transform of y, minus s, y at 0, minus y, the first derivative of y at 0. So, putting this information together, we get this expression, and now, if you observe, the only Laplace transform that is around in this expression is the Laplace transform of y. So we try to have an expression for that, meaning that, okay, so we put together these two terms. That's why we have this s squared plus 1 times the Laplace transform of y here. And then we can put these guys on the other side of the identity. That's why we have this here, which stays the same, and this goes here. So there were negative here and positive in the other side. Okay, and then we can divide by this guy to get this other expression. So the Laplace transform of y at s is exactly this expression times 1 over s squared plus 1. And that was step 1. Step 1 was, okay, I take my ordinary differential equation and I Laplace transform it until I get something like this. The Laplace transform of y at s is equal to some expression that depends on s and the initial conditions. And to get to this expression, we use the linearity of the Laplace transform as a first key, then well-known Laplace transforms, the ones that we saw in the lecture, or maybe you can also use the table that from the textbook. And the other thing that was important here was the property relating derivative of functions and Laplace transform. Okay, step 2. Use the initial conditions to find the Laplace transform of y, like completely the expression. So we know that y at 0 is equal to 0 and y, the first derivative of y at 0 is equal to 1. So we replace this information here. Replacing the information here in this expression, so here is 0, so this guy is gone, and here we have a 1. That's why we have this new expression. Now we can distribute this, for example, and we get this expression here. Okay, again, we started with an ODE with the function yt as the unknown function, the function that we want to find, which is the solution of the equation. Since we want to apply the Laplace method to find the solution, we Laplace transform the ODE and we get this expression for the Laplace transform. And now we want to recover this y of t. So we have to inverse Laplace transform this expression. Okay, so we want to compute the inverse Laplace transform of this guy. And here we use the linearity of the inverse Laplace transform. So these two can go, sorry, first we split the sum and then these two can go out. And now we need to find these two inverse Laplace transforms. Okay, this one maybe you remember that has the shape of alpha s squared plus alpha squared with alpha equal to 1, and then we know that this piece is equal to sine of t. Okay, and then for this one, as you can see here, we have a rational function with a polynomial of degree 0 here and a polynomial of degree 3 here, so we can get its rational fraction decomposition to make easier finding the inverse Laplace transform of this piece. Okay, and that's what we are going to do. So this piece we already know because it's a known Laplace transform. So we already get this sine of t. And now we try to work with the other piece. So the partial fractional decomposition, remember that was a way to rewrite the function depending on the roots that this polynomial has. So this factor will give this term and this factor will give this term. Remember when we have quadratic polynomials with complex roots, then instead of a number here, we have to put this linear function like b times s plus c, where b and c are numbers. Okay, so working a bit here, we get this expression, and then as usual, what we do is to put together all the stuff that is multiplied by s squared, all the stuff that is multiplied by s, and the numbers, and if we have more powers, well, we do the same. Okay, once we have this written, we have to equate coefficients. So here it would be a times a plus b should be 0 because there is no s squared here. C also should be 0 because there is no s here. And then a should be 1. So that's the system that we get, which is written here. Okay, and solving the system, we got these answers: a equal to 1, b equal to -1, and c equal to 0, which give us this other expression. So this other expression of g. Now, when we want to compute the inverse Laplace transform of this expression, it's easier because we use the linearity here. So we split this expression into pieces, and now we know these two guys are well-known Laplace transform. So this comes from cosine of t, and this comes from the function 1. Okay, so putting all the information together, we get that y of t is equal to 2 times 1 minus cosine of t plus sine of t, and then here we just distributed these two. Okay, so in general, this method is, so the goal of this method should be, okay, I have an ordinary differential equation that I don't know how to solve, let's say, so I use the Laplace transform to get an easier expression, and then we inverse this Laplace transform to get the solution. Okay, so in this particular case, we also have the tools that we saw in the first lecture to solve the equation, but now if you're asked to solve the equation with the Laplace transform, then you have to follow these steps. Okay. So a remark here, the property in relating the Laplace transform of derivatives of a function involves these values: f at 0, the first derivative of f at 0, the second derivative of f at 0, and so on, depending on the order of the derivative of f. Okay, depending on also of the order of the ODE. And the previous ODE has initial conditions at t equal to 0. Okay. So for this reason, applying this Laplace transform method was easy because we know the property of Laplace transform with derivatives is given depends on all these values, like f at 0, the first derivative of f at 0, and etc, etc. But if our ODE doesn't have initial conditions at t equal to 0, then in principle we cannot use this as property. I mean, we can use the property, but then we have no idea how much, like the values of this solution, because we don't know the solution, so we don't know the values that the solution takes, the solution or its derivatives take at t equal to 0. So there is a trick for avoiding this situation. Let's see an example where we are not that lucky and we have to do an additional step which is shifting the time variable. So here, okay, we have a second order linear ODE with constant coefficients, and well, okay, this is non-homogeneous because we have a t here, but the difficulty here will be that the time here is not 0, is equal to 1. So the initial conditions are given in t equal to 1. Okay, let's see how we avoid, how can we solve this stuff. This is what I was saying. So the difference here is that the initial data is given at t equal to 1. And we only know how to solve ODEs with Laplace transform methods when the initial data is at 0, because it's related to this property of derivatives, how the Laplace transform acts in derivatives of a function. So the trick is to shift the time with a change of variable. Here in this example, we are going to call tau so we incorporate this new variable tau, and we say that tau is equal to t minus 1. Then when t is equal to 1, which is the original information that we have, tau is equal to 0. Okay. We can also denote theta of tau, y of tau plus 1. So the problem becomes this new ODE with these new initial conditions, this new ODE with these two initial conditions, which are given now at 0 because of this change of variable. So now, and if you remember here, there was a t in the original problem, but t, you can see from here, t is exactly tau plus 1. And that's why we have here tau plus 1. So now we do exactly what we did in the previous example, because now there is nothing to be worried about. We have another e that we can Laplace transform it, and then we can use the initial conditions with the that are given at 0 to find a certain expression of the Laplace transform of theta. So, step 1, Laplace transform the ODE. Again, this is the first step, Laplace transforming both sizes of the ODE. Then using the linearity, we can split this plus this sum and this sum, and these two can go out, so we have these pieces. And of course here we will use known Laplace transforms, and here we will use the properties relating derivatives and Laplace transform. So putting the information together, so we will use these two, the one related to second derivative and first derivative. So we have this s squared, the Laplace transform of theta, and this polynomial of order 1. And relating the first one, only s here, the Laplace transform of theta, and this theta at 0. Okay, so now using these expressions and replacing the information here, we get well, this is already step 2, where we use the initial conditions. So we already know, like, this is 0, this is 0, this is 0. So at the end we will have these two identities. Replacing the information on the ODE, in the once we Laplace transform the ODE and these well-known Laplace transforms, what we get here is exactly this. So the Laplace transform of tau is 1 over s squared. The Laplace transform of 1 is 1 over s. Here we have these two identities where we use the property of the derivatives, also with s, the property of the derivatives and the initial conditions. And now, if you see, we have all this, we have this as a factor common, the Laplace transform as a factor common, as a common factor, so what we get is this s squared plus 2s plus 1 multiplied by the Laplace transform of theta. And here we can compute a little bit, and we get this. And now we divide by this polynomial here, and here there is an s missing. And if we pay attention to this term, this is exactly s plus 1 squared. So what we get is that we can kill this square with this s plus 1. And finally, we get this expression, 1 over s squared times s plus 1. Once we get the Laplace transform of theta, to be able to compute the inverse Laplace transform of this function, we will rewrite this expression using its partial fraction decomposition. So, if you remember that we have to pay attention to this polynomial here. This is a rational function with a polynomial of degree 0 here and one of degree 3 here. So we are in the right setting. And each factor will give us a couple of terms. So this s squared will give us a constant over s plus another constant over s squared. And this guy will give us another third constant over s plus 1. So what I was saying is, okay, this is our function g, and looking at this factorization of this polynomial, we will find numbers a, b, and c verifying this identity. So how to find those numbers? We only need to solve, to work out this piece of the identity and then equate coefficients. So making these computations, what is convenient to do at the end of this computation is detect who is next to s squared, who is next to s, and who is next to 1, or like the numbers. Okay, so now that we have that, we know equating coefficients that 8 plus c should be 0 because we don't have s squared thingy here. 8 plus b should be 0 also because we don't have a term with s here. And finally, this b should be equal to 1. So we get this system that we have to solve. And here we have the answers that you can check if I made a mistake. A is -1, b is 1, and c is 1. So now our function g has this new version, this new expression. It's partial fraction decomposition. Now applying the inverse Laplace transform and its linearity, we can split these terms here. And now we use well-known Laplace transforms. So we know that this piece comes from 1, this comes from tau, and this comes from exponential to the power minus tau. You can check the table that we have at the beginning of the lecture and also lecture 9. Okay, so what we found here is not the real solution, the original one, the one that we really want. It's just this auxiliary function that we incorporate in the problem because the initial data was given in t equal to 1 instead of t equal to 0. So once we changed variables and find this new auxiliary function, at some point we want to go back and find again our original variable t and the original solution y of t. So recalling this identity, tau is equal to t minus 1, we get that the function, the solution of the equation y of t is equal to this minus 1 that we have here. When each time we have a tau, we have a t minus 1. So here is the exponential to the power t minus taus, and that turns into t exponential to the power minus t minus 1. And then you can just work a little bit with the minus and so on, and you find that the solution is t minus 2 plus exponential to the power 1 minus t. So what we saw here in this last lecture was the method of the Laplace transform to solve some ordinary differential equations. The first example was with initial conditions at time equal 0. So we can directly apply all the properties that we know about Laplace transform mainly the linearity, the well-known Laplace transforms, and then of course the properties relating derivatives. And in the first example, since the initial conditions were given at t equal to 0, that was completely enough to find the expression of the Laplace transform of the solution y of t. Once we get that, we inverse Laplace transform to get what we really want, which is y of t. And this expression in general can be obtained using, because we get a rational function, we can rewrite this rational function as its partial fraction decomposition, and then using the linearity of the inverse Laplace transform, we can make easier this finding of the inverse Laplace transform of this expression, so we get this y of t. In the second example, what we saw is that maybe we are not lucky and the initial conditions are given at certain point t0 different from 0. Could be 1, could be 2, could be pi, could be any other number, not 0. And the trick was adding one more step to this process that we just described. And the additional step is that we change variable, we shift the time. So in this example, the initial condition was at time 1, t equal to 1. So our new variable was tau equal to t minus 1. And we solved the equation with this new equation for this new variable tau, repeating the process that we did in the first example. And the last step is going back to the original variable t and the original function that we are looking for, which is y of t. Just undoing this change of variables, as we see here in the last step. Okay, so that was it for today, and this is also the end of the course, so I hope you enjoy it and also you learn this method and some of the other methods that we saw during the course.